This video is for ELEC 1510 Logic Design. This is lecture 13 on sequential circuits corresponding to textbook section 5.2. Rather than being a lecture about math and design, this is more a high-level informational lecture where we're just going to go over a lot of the topics that you'll see in the coming chapter. Let's review combinational circuits before we move on to sequential circuits. Combinational circuits that we've been designing for the whole class so far have a behavior that depends only on the state of the current inputs. That means that any of the intermediate variables and any of the outputs in a combinational circuit will change whenever the input variables change state. If the current inputs change to a combinational circuit, the outputs change regardless of what the time instance is. This means that they can change every nanosecond, every millisecond, every 1,000 years, and so on. For combinational circuits, the circuit itself doesn't remember previous states. So the output can't be a function of what the output used to be. Let's say for a priority encoder, if you had previously received a priority 3 level alert, and now you've taken care of that and moved on to the priority 2 level alert, the circuit won't ever remember that a priority 3 level alert had just occurred. Sequential circuits, by contrast, contain memory elements, so we can construct elements in these circuits that remember previous states. This means that the outputs can depend on the inputs and the memory elements. So the memory elements themselves can act as inputs. Because the memory elements will remember the previous state of the inputs, we'll say that the behavior of a sequential circuit depends on the current state of the inputs and the previous state of the inputs. And it can remember just one previous state, it can remember 10 previous states. It depends how complex of a sequential circuit you design. There are a few different types of sequential circuits. The more basic type is called an asynchronous sequential circuit. For an asynchronous sequential circuit, the outputs are going to depend on the inputs and memory elements within the circuit. So that means inputs and previous states of the inputs. Generally, for asynchronous sequential circuits, we use memory elements called latches to store information. This is not necessarily a strict definition. In some circuits, latches can act as synchronous sequential circuits. In some configurations, they act as asynchronous sequential circuits. Asynchronous just means that the system doesn't respond at a regular interval to a clock signal. Latches in general only change state when the latch is held on. When the latch is off, it remembers the previous state, but it can't change. Asynchronous sequential circuits generally mean that the outputs can change at any point in time, and for this type of asynchronous sequential circuit, which isn't very often used and we won't do much design using this type of sequential circuit, it means that the time delay for remembering a previous state is actually just proportional to the gate delay length, which means how slowly the gates actually change state. The more commonly designed and used type of sequential circuit is a synchronous sequential circuit. Again, the outputs depend on the inputs and the previous state of the inputs. In general, for synchronous sequential circuits, we use elements called flip-flops to store information. The outputs only change when the clock signals change. So in contrast to combinational circuits, sequential circuits make use of a clock signal, and there's a regular timing interval to changing the behavior of the circuit. This didn't really exist in combinational circuits where the entire behavior was designed using a truth table, which doesn't have any time element to it. There's a time element to these synchronous sequential circuits, and that time element is governed by a clock signal. This diagram is taken from the textbook and shows a general overview of a synchronous sequential circuit. In this general overview, we have a combinational circuit. That means the part of the circuit that only responds to the current set of inputs. We have inputs there and then another set of inputs here that comes from memory elements or flip-flops. This is what stores the previous state. So within a sequential circuit, you can have a combinational circuit and then memory elements. The clock signal is shown here, which governs the behavior of the sequential circuit. So let's analyze the clock signal in a little more detail. The clock signal is shown here, and there's a couple different parts of the clock signal that I'd like to go over. First is the low valued part of the clock signal. That's when the value is said to be held at 0. So this is the low value. That could also be thought of as 0. Then we'll say that we have the high value, which is a 1. Now, in general, synchronous sequential circuits don't respond to high values or low values. They respond to rising or falling edges. So a rising edge occurs whenever the clock signal transitions from 0 to 1. So a rising edge is the transition from 0 to 1. And sometimes we draw the little arrow on the rising edge just to indicate that that's the rising edge. Oftentimes, the rising edge is what synchronous sequential circuits respond to. Alternatively, it can respond to a falling edge, which is the transition from 1 to 0. So most clock signals will have low, rising edge, high, falling edge, back to low, and the process repeats. Sometimes synchronous sequential circuits can respond to both rising and falling edges. So we'll talk about how to design circuits that respond to different types of edges in the clock signal in the coming chapter.